Hi, I'm Dave from Soft Shuffle, and this is the technical video. This is where I take a deep dive into how and why Soft Shuffle works. If you've not already watched it, there is an accompanying introduction and overview video which gives a bit more context on Soft Shuffle. It might be worth a watch before this. And also, if you'd rather just understand a bit more about how to use Soft Shuffle, there is a usage video. And with all of those and this, if you want to just read the content, there are equivalent pages with all the detail, maybe even a bit more detail, on softshuffle.co.uk. With that, let's get into what's in this video. What's in the video? Well, we start off with a TLDR of the algorithm, where I attempt to explain the entire thing in under 5 minutes and just about manage it. But also, that does assume a lot of previous knowledge of the subject, whereas the rest of the video is actually an attempt to get you to the point of understanding the algorithm with minimal to no previous understanding of the topics. So that all starts with a discussion, a randomness recap. Then we look into permutations and mappings. We then talk a bit about Fisher-Yates generating a random order and random number generators before jumping to a demo of dealing to order. So that's the same demo that is in the intro video, but we then follow that up with a lot more context. So looking at how we generalize the 2-pass, and then how we fully generalize that to the XPass algorithm. And there are examples in that of how it all works and why it all works. And then we finish off with a little bit of miscellaneous discussion around labeling the mats and things like that. So let's start with the TLDR and let's have a look at the algorithm. I'm going to assume you understand programming for this. If you don't, and if this doesn't make sense, the entire rest of this quite long video is to try and get you there, even if you don't understand programming, to build back up to the algorithm. So, how does the algorithm work? Well, first of all, we use arrays to represent both our mats and the piles on the mats and our decks of cards. So we use the convention that the bottom of the deck is array index 0 and the top of the deck is n-1. And what we have is we start off with array indices 0 to n-1, and we have the array elements be 0 to n-1 as well. We then randomize using Fisher-Yates. But first we need to know how many passes we're going to do. So this algorithm will do an arbitrary number of passes. The number of passes has to satisfy this equation. So the number of piles on the mat that we want to use to the power of the number of passes we're going to do has to be greater than or equal to the number of cards we are trying to shuffle. So once we have used Fisher-Yates to randomize these array elements, this gives us an order we want to deal to. So whatever the value that has ended up at the index 0 is the position, so the index we want that card to end up in. So it's a sorting algorithm. And the majority of the heavy lifting is done by this equation. So our mat representation is a 2D array, and the first index is which pile on the mat. And which pile on the mat we want to deal a card to in each pass is given by this equation. So if we imagine the number on there is the position we want that card to end up in, so the array element at that point. So it will be divided by the number of piles on the mat to the power of the pass number, and the pass numbers are 0 based. So for the first pass, so pass 0, we will get a bit of cancelling out, but generally speaking we do this division and then take a modulo again by the number of piles on the mat. We don't actually need this floor. So this is supposed to be done with integer arithmetic because it's Euclidean maths. However, there is a good chance anyone implementing this is doing it in a language which is quite permissive, and that would be fine, except that we are going to use this position as an array index next. Okay, so we go through and we do a pass, we deal each card out to build up these piles. Then we need to turn those piles back into decks. And so we have this stuff for explaining the gathers. So rather than look at this, I'll explain the underlying, what actually happens. So what happens is you gather backwards, so decrementing or descending your indices, putting the piles on top on the last pass. So the last pass will always end with a gather backwards, but it alternates. So if you have just one pass, it will be backwards. If you have a 2-pass algorithm, it will be forwards, then backwards. And if you have 3 passes, it will be backwards, then forwards, then backwards across the 3 passes. And that's it. It's basically a physical sorting algorithm with a virtual representation that marries the two. And you use Fisher-Yates to generate a random ordering that you then use this algorithm to sort by, or deal to order, as I put it. Now, I went to that quite fast and it was quite detailed. If you just want to look up the algorithm, the TLDR is repeated on the tech page of softshuffle.co.uk. But also, I tend to expect that most people really will want to start from first principles and follow everything through with this video. And with that, on to the full explanation. We'll start our look at how Soft Shuffle works with a bit of a recap of randomness. So we have a definition we're using of fully random, where all output permutations are possible and equally likely irrespective of the input permutation. Okay, so how does our fully random definition compare with physical shuffling? Well, we have a deck like this and we riffle it, so we split it in half and we riffle the 2 halves together. At this point, we know that whatever is in the top of these 2 halves is going to be towards the top of the new deck, the ones in the middle will be towards the middle, and the ones at the bottom will be towards the bottom. We might not be able to predict the exact positions, but we will carry a lot of information through. We are not even at the point where all output permutations are possible. Instead, we will be able to predict pretty well, based on the original deck, where the cards are going to be. Okay, so you will probably make the fairly good comment that, well, yes, that's why we riffle multiple times, throw in overhands and things like that. And yes, we will get to a point where we are moving the cards around enough that all the output permutations are possible. We are going towards what we would consider good enough, where we cannot predict the output ordering based on what the input ordering is. That is not quite the same as saying that all the output orderings are equally likely. In fact, the problem is you need an infinite number of riffles to get to that point. So am I being pedantic with that definition of you need infinite riffles? Yes and no. Although we will get to a point with riffles quite quickly where you are unable to predict the ordering that the cards are in, and we will get to the point where all the output permutations are possible, again, reasonably quickly. That's generally what we're talking about when we say 7 riffles and overhands are good enough for 52 cards. The likelihood of each of those output permutations will still be wildly different. We'll be a long way off them being equally likely. Now, I don't know exactly at what point you get to, I don't know, say the likelihood of each output permutation being within 5% of the average possibility. Is it thousands of riffles? Maybe. Is it hundreds? Probably not. I wanted with Soft Shuffle just to jump straight to they are equally likely. That discussion about when good enough is good enough compared to fully random is part of the discussion about when you would or wouldn't use Soft Shuffle, which I talk about in the usage video. For now, for technical, we are looking at the fact that I wanted to get to the point of fully random and got there, and how we get there. So let's start that off with a discussion about permutations and mappings. We'll now look at permutations, how we can use permutations as mappings, and how this starts us towards full randomization. So for this, let's look at a very simple 3-card deck. So we could label our cards 0, 1, 2, or we could label them A, B, C, if that helps. And when we talk about permutations, a permutation is just an ordering of those cards. So whether you have ABC or ACB, those are two different permutations. So a permutation is an ordering, potentially a specific ordering, and all permutations is the full set of possible permutations, so the full set of different orderings those cards could take. Now when we are talking about input-output permutations, we're talking about the order the cards are in before and after a randomization or a shuffle. So we know with a deck of cards that there are n factorial permutations. So for a deck of 3 cards, that's 3 factorial, which is 3 by 2 by 1 or 6. And so we can see all of these permutations for our numbered and lettered decks. So all 6, the full set of input permutations, and the full set of permutations as output permutations. And what we were talking about with fully random was saying that whatever the input permutation, so whichever of these we start with, we want to always be able to pick each of these and pick them with equal likelihood. Now Fisher-Yates does give us the ability to pick our new output permutation at random unbiasedly with our labelled cards. That is what Fisher-Yates does, more or less, and I'll talk about Fisher-Yates in a bit. And if we'd picked at random one of these labelled cards, output permutations, we would then have to sort the deck to that new order. And actually that's what my algorithm does, and I'll talk about that a bit later. But the problem is we don't want to be talking about labelled cards and picking a labelled order and dealing to a labelled order. We want to be using unlabelled cards. So we're going to be working with unlabelled cards, or we want to be. Being unlabelled, we're not going to know which input permutation it is, so we have to be able to pick an output permutation, and we have to be able to pick all of the output permutations. And we have to be sure that we are picking all of the output permutations, whatever the input permutations, and we are picking each one with equal likelihood. And that's where using permutations as mappings comes in. So what I mean by that is, instead of looking at labelled cards, we're going to look at labelled positions and moving cards between those labelled positions. Now mappings are just functions. In this case they are functions that denote how we move cards from one set of positions to another, so from one permutation to another. And how am I going to show that? Well, I'm going to use these red number labelled cards. So throughout my explanations, I use red numbers to denote the position we want to move a card to. And to demonstrate that a bit more, I'm going to use my trusty numbered mat. Okay, so what are these cards and these numbered piles showing us? Well, what this is showing us, or what this is representing, is us saying we want the card that is at position 0 to end up at position 2, the card that is at position 1 to end up at position 0, and the card that is at position 2 to end up at position 1. Now, we can do this with our unlabeled cards, so we put them out, we go, this card we want to be in position 2. This card we want to be in position 0, and this card we want to put in position 1. And so we have a new permutation. They had an input permutation and they have an output permutation. We don't know what those are because it's unlabeled, but it has them. Okay, well, what if we did that with our letter labeled cards? So A is at 0, but we want it to go to 2. B is at 1, but we want it to go to 0, and C is at 2, but we want it to go to 1. So we knew that our input permutation was ABC, and our output permutation is BCA. Okay, let's scale this up and start talking in terms of full sets. So here we have the full sets of permutations. Let's use them as permutations as mappings. And we are going to start with, just apply them to one input. So I'm going to look at the lettered ones because it can be less confusing than having two sets of numbers, but follow with the numbers if you'd prefer. So what we're saying here is we have our deck of ABC, and they are at position 0, 1, 2 in the input permutation, so the input permutation is ABC. And then we have the full set of permutations but used as mappings here. So if we look here, we have the previous example we had, so we have position 0, 1, 2 is the start, then we want new positions 2, 0, 1, and if we move the cards to meet that, we get BCA. And what we see is, with our full set of permutations as mappings, we get the full set of permutations as output permutations, which tells us, for this input at least, as long as we pick from this set of permutations, and we pick with equal likelihood, then each output permutation is possible and equally likely. And we can scale it up again. So this time we use the full set of permutations as input permutations and the full set of permutations as mappings. And we see what each input permutation used with each mapping gives us as an output permutation. Now this diagram shows us several very interesting things. The first is if we look at these first two columns. So we have every permutation as an input permutation, but only one permutation as mapping. With the set of output permutations that generates, we can see we have the full set of permutations. What does that tell us? Well, that tells us that using a permutation as a mapping, as we are doing here, it is a non-colliding one-to-one mapping. So whatever the input permutation, there is exactly one output permutation, and each input permutation gives us a different output permutation, and we get the full set of output permutations if we use the full set of input permutations and one permutation as a mapping. So if we look instead of as columns but as rows, so let's pick one input permutation, BAC, And we'll look at the full set of outputs when we have the full set of permutations as mappings. And if we look at this row, again we see the full set of permutations. And if we take the time to work our way through all of the input permutations, so all of the rows, we will see that each row does have every permutation as an output permutation. Now that's starting to sound quite familiar, and in fact what that is showing us is that we can achieve our definition of fully random, because all of the output permutations are possible, and assuming we pick our permutation as mappings unbiasedly, and so we pick equally likely from the full set of permutations and use them as permutations as mappings, all of the output permutations are possible and equally likely irrespective of the input permutation. Okay, so we are back to our definition of fully random, and we've shown that we can fulfill this, but we're going to need two things. So firstly, we need the ability to generate these permutations so that we can use them as permutations as mappings, and that's what Fisher-Yates is going to give us, so we'll discuss that in a little bit. And we also need the ability to make this mapping a physical reality, so we need to sort to that mapping, or to put it another way, we need to deal to this new order. And that's what the algorithm I designed gives us, so we'll talk about that in a little bit as well. But first, we are going to need to have a virtual representation of this so that we can do it on our phone. And the software engineers among you will have probably noticed that I am using zero-based numbering for the cards and for the positions. And you've probably guessed that's because we are going to do everything with arrays. So let's talk about how we're going to represent everything as arrays. And I promise to try not to say the word permutations quite as many times in this section. That said, I am going to keep these red numbered cards and the numbered map visible, just as a reminder of what we were talking about in the permutations and mappings section. Okay, so what are arrays and what is our array representation? Now I'm not going to go through all the definitions of what an array is, so it's a basic building block of programming, and look it up on Google. There's a near infinite number of articles on it. But if you aren't familiar with arrays and you just want a definition to get you by, think of them as a row or a column of letterboxes, and each of those letterboxes has an address or a number or what we call an index. So if we have 100 letterboxes, we are still using zero-based numbering, so our letterboxes will be addressed from index 0 to index n-1, which is 91. Now each of those boxes or indices has exactly one thing contained in it. In our case this is a number, and this is known as the element. So we have the array index, which is the address, and the array element, which is the data it contains. Now the notation for arrays is based around square brackets. So when you see a square brackets with a number in it, that's saying it is referring to that index. So index 0 has the piece of data 0. Admittedly in this they all have 0, but we'll come on to that. And that is a one-dimensional array, and we use this to represent our deck of cards or a single pile of cards. But there are also two-dimensional arrays, and take it further, there are multi-dimensional arrays. Now we use a two-dimensional array to represent our mat, which has a set of piles on it, or an array of piles, so it's an array of arrays. If you're unfamiliar with arrays, the way to think about that is now each of our letterboxes contains a set of drawers, and that set of drawers each have their own indices and each have their own elements. So the exactly one thing that our top level array contains is a set of drawers. I won't go too much more into how 2D arrays work because it's a little bit confusing, but just remember that we can use the first index to work out which pile we're looking at, and then the second index is where in that pile we are. And that leads us on to the major convention that we use through this and through the algorithm, which is that the array index 0 represents the base of a deck or pile of cards, and array index n-1 represents the top of a deck or a pile of cards. There is a good reason to have it this way. It's to do with the way we pop and push cards off the top of a deck and deal them into a pile. Look up, if you want to understand that a bit more, have a look on the website. Okay, but what is our array representation? What do both the array indices and array elements refer to? Well, in both cases, they are referring to positions in respect of a card. So the array indices are referring to a card at that position. The array element is referring to a position we want that card to be in. Now, at the very beginning, we are saying that the array indices and the array elements match. We are saying this is the order of our cards. The card at array index is at position 0. Very quickly though, we actually want to change this. So if we think back to our permutations and mapping, what we want to do is randomize where these array elements are, and that at that point they become the order we're trying to deal to. So that is how we are representing our randomization. Now hopefully this page will make everything a bit clearer. So this represents the randomization step. So if you remember at the end of permutations and mapping, we were saying we want a way of randomizing our mapping, and then we want a way of dealing to that new order. So this is the randomization. We are taking all of our elements, which are from 0 to n-1, which matches the indices that we have, so 0 to n-1, and we are randomizing them. And I'll talk about Fisher-Yates in a minute. At this point, we have a representation of a theoretical deck of cards where the deck at index 0 wants to be sorted so that it is at index 91. Now if we again refer back to our permutation and mapping and what we were talking about, if we can deal to that order, then we are happy we have fully randomized it. So what does the dealing look like using this pictorial representation? And the second diagram is a high-level representation of dealing to an order. So what we have, we're saying our card that is currently at index 0 wants to end up at index 91. The card that's at index 1 wants to end up at index 94. And we've done a deal or a sort or in some way organized our cards such that that card is now at index 91. So it's somewhere in here. And all these cards are cards that started at different indices. So the card that is now at index 0, where we've made it match, we've moved it around, will have started off at a different index somewhere here, and we've dealt it such that it's ended up at the bottom of this pile. So yeah, we then have two high-level diagrams to represent the two halves of Soft Shuffle. So we have the bit that I've described as generating a new random order, so starting with the cards in their original order, generating a new order or a new permutation that we can then use as a mapping. We then take that new ordering that we want to deal to and we deal to it. And if we remember what we talked about in Permutations and Mappings, that's what we need to get to our definition of fully random. So now we need to implement both of these things. Okay, so let's look at the first of those two. Let's look at Fisher-Yates and random number generation and how we can make this top level diagram a reality. So what is Fisher-Yates? What is this algorithm I keep talking about? Well, fundamentally, Fisher-Yates is an algorithm for shuffling or randomizing a finite sequence. So that sequence could be the order our cards are in, or it could be the order of a set of positions. And for our implementation, we're using it to shuffle or randomize the elements in an array. So the way Fisher-Yates works is we iterate through all the indices, and generally we start at n-1, and for each index we generate randomly a new index from 0 to the index we're looking at, and we swap the elements at that. So if you generate the index you're working on, then obviously it's a null operation, and then we move down and we do the same for the next index. So generate 0 to itself. If it's something different, you swap the values and you keep iterating through the indices until you've done all of them. And at that point, you have fully randomized your array elements. And that's about all I'm actually going to say about Fisher-Yates in terms of what it does. The reason being, there's a very good explanation of what it is on its Wikipedia page. It is an algorithm that's been around for a very long time. And the link to that is on the technical page. The important thing we need to take away from Fisher-Yates, though, is that given an unbiased random number generator to pick which of our set of indices to swap with, given an unbiased random number generator, it gives an unbiased randomization, which means we have coalesced our problem of generating a new random order to deal our cards to down to having an unbiased random number generator. Now there are a few implementation details with Fisher-Yates, so there's out by one errors you need to watch out for, that kind of thing. And that's one of the reasons why the source code for the core of Soft Shuffle is on GitHub, and there's a link to that on the technical page. But for now, we are happy that the next step is we want an unbiased random number generator. When we are talking about an unbiased random number generator on a computer and getting to that point, we are generally talking about an algorithm based on a family of algorithms known as pseudo-random number generators, or digital dice, and I will put my trusty D100 there to help me remember what I'm talking about. So pseudo-random number generators, they work by having what's known as a seed. So this is generally a very large number. You then take that seed and use it to seed a bunch of state within the pseudo-random number generator. You then run the pseudo-random number generator, and that state gets munged, processed, mixed around, all this kind of thing, until you are happy you have done enough pre-work, let's call it. At that point, you go to your pseudo-random number generator and go, give me a stream of bits. So in the ideal case, that stream of bits, each bit has no relation to the bits before or the bits after. And actually, nowadays, pseudo-random number generators, even the much maligned math.random, aren't that bad. They are, for most things, actually more than sufficient. However, they do have some subtle sources of bias, especially if you're using them for something like Fisher-Yates. So there are three main ones. So the first is the kind of cyclical problem of picking your seed in the first place. So you have a situation where you need a seed to generate a set of random numbers, but you need a random number to generate the seed. So what do you do? And I'll talk about that in a minute. And the other, even more subtle one is, let's call it permutations or cyclical, the cyclical nature of pseudo-random number generators. So there was research reasonably recently proving that the number of possible permutations you can generate from the state within a pseudo-random number generator is directly derived from and proportional to the length of the seed, so the number of digits of the seed, the maximum number the seed can represent. That's a particular problem for Fisher-Yates. So the reason is the number of possible permutations you can generate from a pseudo-random number generator will directly determine the number of permutations you can generate from Fisher-Yates itself. And the third problem is a classical scaling problem. Now, the scaling problem I'm going to talk about separately in a minute because we deal with that with implementation. But for the first two, so picking a seed and the cyclical nature of pseudo-random number generators, we solve by using a class of algorithm known as cryptographic random number generators. Okay, so how do crypto-random number generators solve these problems? Well, in essence, they are pseudo-random number generators, but they are pseudo-random number generators with a healthy dose of entropy, or randomness, mixed in from both the hardware and operating system. So what that means is we mix in values of temperature, values taken from sensors, things to do with cache. There are a whole bunch of stuff, and there are some nice articles on how hardware random number generation, which is fundamentally what this is. For our purposes, though, we don't have to deal with any of this. Cryptographic random number generators exist and are accessible from web pages for a very good reason. We need them for internet security, for generating keys and the like. So we don't actually need to do anything to get this benefit, but it is useful to understand why it solves our problem. So the first problem we were talking about was randomizing the seeds we use. So cryptographic random number generators solve that by, when you seed them, they use a lot of entropy to pick that seed. It is extremely important that they are done that way, but it is all done for us. And the other is the cyclical or permutation problem. So the fix is slightly more subtle, as well as the problem being slightly more subtle. So as a crypto-random number generator is running, the state that I talked about that a pseudo-random number generator has gets modified with entropy from the system. So you actively mix entropy into the state. That fundamentally just solves the problem of the cyclical nature of pseudo-random number generators. They can't be cyclical if you change them, especially if you change them with a source of entropy. And that leaves us with scaling. So what's the problem with scaling? So to explain this, let's look at our trusty D100 and imagine we're using that to pick an array index to swap with. So we've got 100 faces on our dice, and as long as the range of the array indices we're picking from is the same, so 0 to 99, it's going to be fine. There's not going to be any bias from doing that. I mean, that does assume that our dice is perfectly balanced and in no way weighted, perfectly machined, but let's pretend it is. So that wouldn't introduce bias. But let's look at the case of where we want to generate an array index between 0 and 73. Okay, well now we have to do something with our outputs to make them fit that range. So the very bad option would be to just wrap around the numbers. We'll ignore that. That's massively biased. The other way we might naively choose to do this is to scale them. So scale the values from 1 to 100 down to 0 to 73. The problem is that requires rounding, and rounding is always going to introduce bias. That is a product of that kind of quantization. Okay, so what can we do instead? Well, actually it's quite simple. We say, is this value in the range we're trying to generate? No? Well, we'll just re-roll our dice. So that's known as rejection sampling, and it works. So the problem is obviously you need to keep re-rolling it if you get the wrong values, and I'll talk about that a bit more in a second. So how does rejection sampling work with what we get out of a crypto random number generator? So the values we are requesting are uint 16s. So a uint 8 would only give us 0 to 255, and we obviously potentially want more than 250 cards. A uint 16, however, gives us 0 to 65535, if my powers of 2, I remember them correctly, which is more cards than we're ever going to use. At that point, you are probably quite reasonably saying, well, if you're only generating values 0 to 73 and you're rejecting the ones not in that range, that's almost all of the values. And that's true, but it's fine. So we get around that using binary masking. I guess you could call this binary masked rejection sampling or something like that. So what I mean by that is we generate our uint 16, and of that we only care about the number of bits that are the minimum needed to encode the highest value of the range we want. So if we're generating 0 to 73, we want the minimum number of bits that can hold the value 73. So we know that's not 6, because the maximum that 6 can encode is 0 to 63. But 7 is fine because that can do 0 to 127. So we say, okay, we only care about 7 bits. And we create a mask with zeros for all of the bits other than the first 7 digits, and we use ones for those, and we do a logical and that's it. We've essentially scrubbed the rest of those bits, and we can look at the value that is given by our masked uint 16, and that value is 41, which is within the range 0 to 73. So that's fine, we're happy, we can use that. The implications of doing this kind of masking is that the chance of rejection is always going to be less than half, which means the number of rejections, so the number of times we need to re-roll in essence, so take another randomly generated number, on average is less than 1, so it's less than 1 repeat. That's fine, because in the grand scheme of things, the number of random numbers we actually need to generate for this is quite small, in computing terms anyway. If you need to randomize even 1,000 cards, 1,000 random numbers to generate is not very much in computing terms. And that's the other reason why we do this way and don't treat it as bit streams. I mean, we could take all of our uint 16s and generate and squish them together into a bit stream, and just take off the number of bits we need and use those. But it's unnecessary. It's not going to tax a computer to do this. And as far as I'm aware, currently crypto.random in JavaScript anyway doesn't have a bitstream option, or just use that. Okay, so with that we have talked about how a crypto random number generator gets around the seeding and cyclical problems of a pseudo random number generator, and we've talked about how we can get around problems with scaling bias using rejection sampling, which leaves us at the point where we are happy to say that using all these techniques we can generate unbiased numbers from our random number generator, and we can apply them in an unbiased way to our Fisher-Yates algorithm. And we said that if we are using an unbiased random number generator in Fisher-Yates, then the randomization it generates is itself unbiased. Okay, well, we've also said that if Fisher-Yates is an unbiased order generator, and we use that to generate a reordering to deal to for our cards, if we remember back to permutations and mappings, we're happy that as long as we can deal out to that new order that we've generated, we are still on track, we are still fulfilling our definition of fully random. So with that, let's look at dealing to that order. Okay, so dealing to an order, or the fun bit of the algorithm I designed. So if you remember our high-level diagram, what we're saying is we've generated our random order using Fisher-Yates like we just talked about. And for example, we want the card that starts at index 0 to end up at index 99 at the end. Or if we remember back to our cards in permutations and mappings, we want the card that is at 0 to then end up at pile 2, the card that is at pile 1 to end up in 0, and the card that is in pile 2 to end up in pile 1. How do we make that happen? Well, to give a visual demo, I'm going to start with the deal to order demo from the intro video. Now, the easiest way to demonstrate this is to use a very specific instance of the two-pile shuffle. So it's very specific in that we are using a map with exactly 10 piles and exactly 100 cards, which means that the numbering of our mat and our cards lines up with our normal decimal counting system. So we have 10 piles, and they are labelled 0 to 9, and 100 cards labelled 0 through to 99. Now, you'll notice that this way around, these cards are in order. The numbers are from 0 up to 99. That's just to show us the original order. So the original order, as I flipped it over, is 0 on the bottom, 99 on the top. The new order, however, is red numbers. And so we want to deal to this new order. We want to make these numbers be 0 at the bottom to 99 at the top. And because we've generated this order randomly, that will randomize our deck of cards. So for the first pass, we are going to sort by, and this is a partial sort, the first digit. And in the second pass, we're going to deal by the second digit, or the tens value, so tens and ones. This works because the two-pass version you can think of as dividing the position we want it to end up by the number of piles. But we've set the number of piles to 10, which means we don't have to do any difficult maths on each card ourselves. We can just look at what is the number of the card divided by 10? Look at the remainder. What is the number of the card divided by 10? Look at the quotient. And it works the same for the general 2-pass case, even if we have, for example, 9 paths and 0 to 8. It's just that we would have to divide 85 by 9, and that is going to break my brain very quickly. Now, the full general case, where we do anywhere from 1 to 3 or 4 or 5 or how many passes, isn't quotients and remainders. It's modulo of a division. It just happens that it cancels down to quotient and remainder for 2-pass and is a lot easier to understand what's going on. So okay, let's get dealing. And a little bit of supplementary voiceover from me. So first deal, so we're dealing by the ones value or the remainder if we divide by 10. And the thing to notice with this is the cards are accruing in piles at different rates. So some piles might have 2 or even 3 before any go into some of the other piles. Now, this is because obviously the numbers are random, as in the ordering is random. So if we are sorting them and we are partially sorting them, they are going to be accruing at different rates. So the other thing you might notice is me occasionally pausing while I'm doing this. It is actually quite difficult to do this compared to Soft Shuffle, because for each number you have to look at the number, go, which pass am I doing, so which of the digits do I care about, and then the piles are numbered rather than letters for row and numbers for column, which means you have to work out is it top or bottom of the pile. So it's non-trivial to do this, and it's actually much easier to do Soft Shuffle because you just look and deal to that space. And now we'll fast forward through the rest of this, and we'll slow down towards the end of this first deal. Now we've finished the first deal, and we can look at the cards in pile 0, and you can see it is all of the zeros, so first digit is 0. We now collect them up or gather them. I call this gathering forward because we are gathering from piles with an ascending number. And we can start the second deal, so dealing by the second digit or tens value or quotient if we divide by 10. And I'll just pause it here. So you can see that we now have all of the zeros and they are ordered, so 0, 10, 20, 30, 40. And if we carry on, we can see that we are now doing the ones. And you quite possibly at this point are starting to guess where this is going, because we're going to end up with exactly 10 in each pile, and because we have ended up with the zeros at the top of the deck in the first deal, so for the beginning of the second deal, we are going to stratify all of the zeros, and then we stratify all of the ones, and then we stratify all of the twos. And if we only have as many stratifications as our number of digits, because we're doing decimal, we then have fully stratified the deck. So yes, I'll fast forward through the rest of this. And slow down as we end up dealing out the nines. And there we go, and we can see that in 0 we have the numbers 0 to 9, and they are nicely ordered. And look at the other end, and we've got 90 through to 99. And so it is simply a case of gathering these back up, but we gather them backwards, so descending numbers. And that's it. We have fully sorted this deck by the red numbers. So 99 at the top, 0 at the bottom. And just to show what we've done, we will take a look at the black numbers, which it was ordered by originally, and compared to those now appear to be in a random order because we have randomized the deck, because we have dealt it to a random order. Hopefully it is fairly obvious that our deck with red numbers that we have sorted to is in fact our diagram from earlier in physical form. So we have the black numbers, which were the array indices at the beginning, and then we have the red numbers, which were randomized at the beginning, and then we dealt to, so sorted to that order. Okay, now let us look at the general 2-pass case and also at the even more general X-pass case. Okay, let's jump straight in with the 2-pass algorithm and the pseudocode for that algorithm. And I'm going to bring along a card to help me. And to help with this, I have highlighted the important bits. Okay, so what are they? Well, first is, this is the first pass, so the first deal. And what it's saying is map position is which of these paths to deal it in, so the index of the map pile. And it's saying to use the deck position, the value that is at deck I, which is this number, and to have it modulo the number of piles that we have on our map. So 10 for our 2-pass, so if you imagine it is 8. And so a couple of things to mention at this point. So the floor that we've wrapped everything in, I'm going to talk about that in a sec. And modulo. So modulo and remainder are the same only if you're talking about positive numbers, but we are talking about positive numbers, so we can use modulo and remainder interchangeably. And to explain it a bit more, so what if we were using 9 piles? So we want 58 mod 9, and that would be 58 divided by 9, and what is the remainder? So assuming my mental math is right, the remainder is 2, so this would end up in pile 2 in a 9-pile deal on the first pass. Okay, so then we look here. Now this is our gather operation, so this is gather forwards. It starts from n-1 to 0 because although we're doing take a pile, put it on here, put it on here, put it on here, that's the same as taking this pile, putting it here, taking this pile, put it on top of that, taking this pile and put it on that, and that pile and put it on that, which when we're using pop and push operations is how it works. Okay, so we come to the second pass. So again, map position, so which index in our mat array we're dealing this card into. Deck I is this number, and we divide it by the number of piles. So if we're using our 10 piles, 58 divided by 10 is 5 remainder 8, and that, or 5.8, and that kind of brings us to floor. So we shouldn't need the floor. We don't need the floor, assuming that we have forced integer calculations, because we are supposed to be doing this. This is Euclidean maths, this is integer maths. I am and ah about including the floor, but my expectation is if someone watches this video or reads the sites and then goes off and tries this, they're probably going to try it in something like Python or some other language which isn't strongly typed, and you're immediately going to run into the problem of using a non-integer as an array index, and we don't want that. So I'm including it there as kind of a safety net for anyone that's implementing it, but you don't need it. You shouldn't need it. And the reason you shouldn't need it is because we are specifically saying you can only do cards that are up to the value of the number of piles squared, so you don't get any of the overflow that it would cause an issue that the floor would be hiding, for example. Okay, so we've done that, and yeah, 58 divided by 10 is easy. If we're using 9 piles, it would be 58 divided by 9, and I can't remember what that is off the top of my head, but it will end up in whatever pile is the integer division we get from that. Okay, and then we just have the final gather, and this is showing us it is a reverse gather, so going this way. Next, let's look at why this works. So, get out my diagram. This shows us a number grid for a 9-pile 2-pass sort or soft shuffle algorithm. So what it's showing us is 9 piles and 81 cards, because 9 squared is 81. And what it's specifically showing us, so this is one very specific permutation that I've picked, but it's to show one specific thing, which is in the first pass, all these numbers end up in the first column, which is the first pile, or the 0th pile. And all of these numbers end up in the last column, or the last pile, or the 8th pile. And it's showing us that these numbers, so 0, 9, 18, 27, etc., this set of numbers will always end up in this column after the first deal. Yes, they're in an order in this example, because I picked this example so I can show the numerical relationship, but fundamentally this set of numbers will always be in this column after the first pass, this set of numbers will be in this will be in this. And then what it shows us, so we pile forward, so these end up on the top of the deck, and then that means they will be the first to be dealt, which means in the second pass, that set of numbers gets dealt out here. So we have partially sorted them after this pile by sorting them into these sets of numbers, and then we pile them up so that this set of numbers is at the top, and then because they are the first to be dealt, they will end up at the bottom of these piles in pass 2. And we can see how we end up with our stratifications. So all of these numbers, this set of numbers, end up in this column, and then they get dealt out in this stratification. These ones would end in this stratification, this one would end in this stratification. And we would have this this kind of number grid for any 2-pass algorithm based on how many piles it has. So an 8-pile one would be like that and smaller, etc. Now a reasonable question at this point is, what if I don't have 81 cards but I'm still doing a 9-pile 2-pass algorithm? Well, in this one we have 0 to 49, and what it's showing us is we still have the same numbers, but it's the subset of that those numbers that exist in 0 to 49. So in the first pass, they still end up in the same columns. Obviously, they will drop down, and the piles will be smaller on the end and slightly bigger here, but still not 9. And then we pile them up, and then we deal them out. But our stratification still works because we don't have more than 9 squared. So those end up in that pile in the first deal, and they end up stratified at the bottom again. And then when we pile them up, we will see that the numbers end up. That should give a good explanation of how the 2-pass works. If it's not fully sunk in, I would say go to the technical page on the website, so technical on softshuffle.co.uk. I go through it in a bit more detail, and as well as these, let's call them theoretical 9-pile, there are worked examples where I've taken a randomise order and I've done these diagrams, but with the actual randomized order, and you can see how all the cards go through. So let's take a look at the X pass. And now for the XPath version, or the full general algorithm. And just like high school science, what I just told you was a simplification, but a useful one. And we'll talk about why it's a valid simplification in a bit. So I'm going to talk through the algorithm, and it's 2 pages, this one. This first page is mostly setup, so we need to pick the number of passes, so it's the lowest number that satisfies this equation, and you can see how the 2 pass, so number of piles on mat squared, or to the power 2, is greater than or equal to the number of cards. Yeah, it's the same thing but extended, so that we can do 1 pass, 2 pass, 3 passes. It'll do 4, 5, 6 or whatever number of passes, but we obviously don't really need that. And then, yeah, you use Fisher-Yates to randomize the deck, to randomize the numbers and the order that we want to deal to. And then this is the first interesting bit. So we are going to use the number of passes now. So this is saying that if the number of passes is even, then the first gather will be forwards. So remember, our 2 pass we gathered forwards on the first pass and backwards on the second pass. Well, the generalized case is that you always end up gathering backwards on the last pass you do, and it alternates before that. So on to the second page, the interesting stuff. So here's where we get to the meat of everything. So again, as before, mat position is the index on the mat of the pile we want to deal to, and floor, it's only really there as a helper. We don't need it because we should be doing Euclidean maths, and we should be using integer functions, so that it's fine with using it as an array index. But this is the important bit. So what it's saying is this number, so the position in the deck we want to deal to, we divide it by the number of piles on the mat to the power of the pass number. So in pass 0, because it is 0 based, that will be 0, and anything to the power 0 is 1. So it becomes this value divided by 1, which is itself mod the number of piles on the mat, which will sound familiar, and we'll come back to that. But then when you're doing the second and the third pass, this becomes more interesting. So we calculate this, and it will be different each pass, and so we get our multiple partial sorts done by this. And I'll talk through how or why that works again in a second with an example like I did with the 2 pass. And then we come down to the bit that does the gathers. So this is the second half of what I was saying before. So we always end up with the last pass we do being a backwards gather. So if you remember our 2 pass, that is true. But in a 1 pass, it will only be a backwards gather. And in a 3 pass, the last one will be backwards gather, but it alternates. So the first one's backwards, the second one's forwards, the last one is backwards. And just like with the second pass, we have a theoretical example to talk through why this works. So this is like our 2 pass 9 pile explanation, except more complicated. This is 4 piles, 3 passes, 64 cards. So the most cards you can do with 4 piles in 3 passes. The way to think about this, or the new thing to take on board, is we are doing multiple partial sorts. And if you could extend this to 4 passes, and you would be doing even more partial sorts. And the way to look at it is we are doing partial sorts of groups of 4 because we have 4 piles. So again, we start with a column, and this again, all of these numbers, whatever the permutation of the 64 cards, this set of numbers in a different order will end up in this column. So they'll end up in this column in who knows what order, but then the subsets of 4 within this subset of 16 will end up at this bottom row, bottom 4 rows after the second pass, after the second deal. And they will end up in these little subsets of 4, but again, these little subsets of 4 won't be ordered. They won't get ordered until the third pass, where they will get ordered into their stratifications. Now, this is definitely one where I would say go and look through the worked example on the website where I take a proper randomization and we follow it through, because it becomes really obvious how it's working then. But you have to think, well, I'm doing subsets of subsets. So I sort into my subset of 16. I sort my subsets of 16 into subsets of 4. And there will be 4 subsets of 4. And then I sort those subsets into their stratified rows in the third and final pass, which is quite a lot. And again, I say the best way to understand this, if it's not clear from this, is to go and look through the worked example. But again, like before, we want to see what happens if we don't have the full number of cards, if we don't have 64 cards. And again, it works. It works because although we don't have all of the cards that would end up in that subset, all of the cards that are a partial subset end up in our partial subset here, and then they get dealt out into their partial subsets, and then they get stratified normally. So yeah, that's all fine. Now, the eagle-eyed amongst you will have noticed that our 2-pass simplification doesn't actually quite match the 2-pass version of the X-pass. Okay, so let's look at the simplification and see what's going on. Alright, so for the first pass, and this will be true for any first pass, even if we only have one pass, which is the first pass. So we have our map position, so where we want to deal our card to. We have our array element, which is our number we want to deal to. And when we have number of piles on the mat, so our number of piles to the power of pass number, so the pass number is 0, anything to 0 is 1, so anything divided by 1 is itself, so we get to the value modulo the number of piles on the mat, which does match, so that's fine. With the second pass, be that the second pass of 2 or the second pass of 3, we have a pass number of 1, and so anything to the power 1 is itself, so we have the value divided by the number of piles modulo the number of piles on the mat. But we didn't have a modulo in this one. It doesn't matter, is the reality. It doesn't matter if we're only doing 2 passes. And the reason is, if we're only doing 2 passes, then this value, our number, we've said will never exceed the square of the number of piles of mat. So if we're 0 based, it will never equal that value. But if it never equals that value, then when we divide it, we never get any wraparound for a modulo to have to handle. So we don't need the modulo in the 2-pass version. So it's fine. We can just ignore this for the 2-pass version. And we do that because it makes it easier to explain. So we've done it. We have our generalized XPass algorithm, and with our set of cards that has a set of elements that we've randomized, we've shown how we can deal to the order of those elements and make it real, even if we have more cards than the square of the number of piles. So realistically, any number of cards we can make it work for. Just vary the number of passes. Okay, so we've made this work, and we showed how we could get to that point with Fisher-Yates. And with what we had in permutations and mappings, we showed that with those two, we can say we've achieved full randomness. So with those both together and with the explanation in permutation mappings, we can now say, yes, I can randomize a set of cards such that all output permutations are possible and equally likely, irrespective of the input permutation. We've succeeded, but there are a few loose ends to tie up. So obviously our explainer mat has numbers, but our actual mats have alphanumeric labels, so we need to talk through that. And I'm sure there are some of you that would be interested in running the code and would like to see what logging I've put in, because generally the best way to look at code is to run it and read the logs. Well, we'll cover all those little bits in the next section, the miscellaneous stuff. Okay, so throughout most of the video we've had our trusty numbered mat, but obviously we actually use the alphanumeric labels that make it easier to pick which row you're on and which column. So how internally do we go from the array index representation to the labels? It's just a lookup table. There's nothing complicated about it. In fact, that's all there is to it. The only thing that's interesting is that does make it easier when we come to do the next steps with Soft Shuffle. So if we're looking to do animations or audio or that kind of thing, having an internal representation that we can then just hook up a different lookup table to, or look up different animations or what have you, will make that easier. And that just leaves source code and logging. So there's not much to say on these either. There is a link to the source code on the technical page of softshuffle.co.uk. It's hosted on GitHub. It's there for a couple of reasons. The first is obviously people are probably going to want to have a look at how the code runs to verify all the things I've said in this video. But also I've deliberately designed it to be a single page so that you can download the single page and use the shuffler offline. In terms of logging, so your best bet with the logging is going to be running it on a desktop browser and going into developer options or what have you, so you can see it. It logs to the console. The logging itself should be fairly self-explanatory. It's probably easier to understand exactly what it's doing if you've got the code in front of you as well, but more or less you can see the card numbers or the order you're dealing to come up, and then see how they move around, and then see that they get to the order you want. You made it to the end of the video. Thank you and well done for sticking with it. I do appreciate there is a lot of dry technical detail. It is quite in depth, but that is what is necessary to make the claim that Soft Shuffle lets you fully randomize a deck of cards. If you do have any comments or questions, please comment on the video, reach out on social media, reach out on the website. And with that, thank you, and go play a game with fully randomized cards.